Cool. Just quick recap what we've done 2 weeks ago. So we were basically talking about, two different kinds of representations. One on the symbolic side, which we covered a while ago, and then we talk about the audio domain representation. But basically, MIDI-like piano roll, and that translate to, in audio domain, time series like waveforms and image-like spectrograms. So we talk about, sampling rate, where you basically need to quantize both the temporal but also the amplitude axis of a signal so that you can, store them on the computer. That's the big question because we want to digitize everything. And we talk about, bit depth, where we look at the resolution on the amplitude side. Cool. And we talked about this sampling theorem. So this is likely one of the most important concept in this whole, sampling theorem. So basically what we want to see is that in order to capture a signal at, Fs, we need at least twice the sampling rate, twice the frequency for the sampling rate, so that we can critically sample that signal so that we can reconstruct it perfectly. If we undersample, then we cannot reconstruct the original signal. So that's pretty much the whole idea of that. And we talk about FFT, and that's likely something you've looked into in PA2. So basically, what we want to do is to, decompose the frequency components of a signal. So in this case, look at it, couldn't really tell what are the frequency components. Maybe you could tell that there's some 2 Hz going on because there's roughly this shape. But for other parts, it's very hard to do it. So basically, that's the idea of Fourier transform. For Fourier transform, we basically take different frequency components, and we try to match whether they have that components inside the signal. And then we talk about short-time Fourier transform. Basically, we just slice the audio into chunks and apply Fourier transform so that we can localize, which frequency components happen at which time. So, in PA2, you've seen, not PA, yeah, PA2, you've seen, we go from, FFT on the whole signal, and you couldn't tell what exactly it is about. But if you take the first 200 millisecond, then now you see the frequency component of that 200 millisecond. So SDFD, basically, you just slice through it so that you get, at each position, you see where that frequency components change over time. So that's how we get the spectrograms. So, one of the most important part is that if you're listening to music or any, harmonic audio, even speech is harmonics, just a little bit different from music. But basically, you will see the fundamental frequency and all the harmonics. And that's what, determine the timbre of the sound that you hear for speech, for, music signals, and everything that's harmonic. Cool. And at the end, we show this image that sounds, which is pretty cool, where you sort of can get both, can get the best out of the both worlds, where you have an image that look like your prompt, but at the same time, you also can hear that sound. This sounds right. Anyway, cool. So today we are going to jump deeper into what's deep learning and to get more into the technical part of that. Any questions? Cool. So PA2 is due today. So remember to upload that. Cool. So basically the idea is that, this is not a deep learning course, but basically what we want to do is to sort of scratch the surface of deep learning and get all the, necessary knowledge to so that we can proceed onto the rest of the course. So, this will be a very high level overview of what deep learning is and what are the most important concepts are. We won't go into detail, how to essentially, train a model. We will touch on it later on, and we will have a homework to give you a flavor how to train a deep learning model. But for most parts, we will be looking on, what's the concept of deep learning and what's the concept for, machine learning. Cool. So what is deep learning? We've talked about, again and again, AI versus machine learning versus deep learning, because I think that's important because that sort of like give you a little bit context of the history, but at the same time, hope to provide you, and a perspective of how things evolve and also how things are different from one another. AI is everything that just exhibit intelligent behaviors, could be like human or not like humans, but it has to be somehow intelligent. For machine learning, it's everything that learn from data. So this is much broader than the strict definition of deep learning nowadays. So algorithm that learn from data using deep neural networks. So deep learning is by definition a subset of machine learning. So there's a lot of like machine learning models. They just need to learn from data. It doesn't necessarily need to use deep neural networks. So that's different from that's the difference between machine learning and deep learning. So we talk about this a little bit about the components of a machine learning model. So basically, this is the definition of it. I think pretty precise. So you want to improve on tax T with respect to performance metrics P based on experience E. So this is important because like if you look at a machine learning model, if something is missing, then usually typically that means that that model is not a machine learning model. So usually, sometimes you won't see, experience E. So a model is just like doesn't really look into the data and somehow it just, improve on text team, then that's when we call it is like an optimization algorithm rather than a machine learning model because it's not learning from data, but rather it's just doing some optimization. Sometimes performance metric P is, missing where you don't really have a way, to evaluate a model. So your model is not technically learning something because there's no way you can measure whether it's learning something. You couldn't see whether the performance is improving. So every single words here is very important. So TXT usually define the inputs and outputs. That's very important. We will see again and again, especially in the deep learning era, because all the deep learning model is just simply a function of mapping between inputs and outputs, as we will see later. Performance P is the objective function, loss function. We will get to it again and again, which is the most one of the most important part of the machine learning model, but also a deep learning model. And experience E, basically, that's just the training data that your model is learning from. And by improve, we just need to do a bunch of optimization. So these four, components basically capture most of the parts of machine learning model. So what is deep learning? Basically, I think we've also touched on this. It's just a type of machine learning that use deep neural networks. So this is deep neural networks. So let's take a look. So we have some input layer where, those are just some numbers, whatever those are. And we also have some output layer that will be some other numbers. So think about, the input layers could be, maybe you want to I don't know, determine the age of a bear, that you have some video on the bear, or you have some information about the bear. The output layer would be the age or maybe the weight of that bear. You have some input layer. You would have some variables that you collect, some data you collect, say, running speed or, how frequently, how long they sleep, stuff like that. because you couldn't really, approach them to um, you know, measure their weight, but you could, try to have a model that estimate the weight of a bear. So basically, these deep neural network is just a mapping between the input to the output. And everything in between are called hidden layers. And each of these things are called neuron. So I think we've touched on this. But basically, inside the neuron, what is going is basically a linear mapping, not essentially linear. So linear weighted sum of all the inputs. So we have x1 all the way to xn, and there will be, weighted by different weights. So we have like W1 to Wn, these are different weights. So you have a bunch of inputs. So think about the case, when you want to estimate the weight of, some input variables, say how long they sleep, how much they eat, stuff like that. So you want to take into account how these weights affect the output. And we also added, a bias term because, when everything is zero, there still might be something. And then we have this activation function, which look like this. We will get into this later. But basically, they will turn, these things into 0 to 1 for the output. So this is basically what it looks like for a neuron. So we can write it into something like this, a weighted sum of all the inputs value, x1 all the way to xn, weighted by w1 to wn, and plus b. So this is basically, a linear combinations of all the inputs plus a bias term. And then it will go through this, activation function so that you get the outputs. So oftentimes you will see something like this, looks horrible, terrible, but it basically is just this in a fancier way. And then you can even write it into, a dot product between a vector. So again, this is just a way to write these into, even more compact form. So we can actually compare an artificial neuron to a human neuron to get a sense, why artificial neuron take these shapes. There's some reason why we design it into this. So think about a human neuron is that, a neuron will be connected to different other neuron. So you will actually receive, electrical signals from all the surrounding neurons that connected to this single neuron. So this is the, the nucleus, the cell body, the central part of a neuron. You will receive a bunch of other, electrical signals from the early surrounding cells, neuron. All the other surrounding neurons, they are cells as well. So now you want to determine whether this is important enough. So you sort of think about it, you got a lot of like different signals coming in, alarms coming in, and you want to determine whether all of these things have reached the threshold of, sending out an alarm. You want to keep it, or these could be just false alarm. So the idea for human brain is that, we will just keep, think about all these different, incoming signals. One signal, it's like false alarm. The second signal is still false alarm. The third signal is still false alarm. But the fourth, signal come in, now it reached that threshold of sending something out. Then that's when we said that's the threshold potential. So if there are multiple, signals coming in almost at the same time that accumulate above this threshold potential, then, it will generate this successful initiation. And this is what we call an action potential. So this basically will just send a signal out. So you can think about it as like a sort of like explosion, or, basically just trigger a signal that will send out to the connecting cells. So basically that's the idea of human neuron. You want to sort of filter out false alarms, and you only want to shoot something when there's enough alarms coming in that together go above the threshold that you have. So that's basically how we can build this artificial neurons. So look at how we collect all the different signals. Now the difference between an artificial neuron and a human neuron is that human neuron will just accumulate them together to see whether they go above the threshold. But for artificial neuron, we actually also trying to learn these weights so that we can, take into account of different input signal, and we try to adjust their importance in triggering our signal. And for the threshold potential, as I said, once we reach some level, we will send a signal out. So there will be a 0-1 switch. Everything below the threshold potential, we will send nothing. Anything beyond the threshold potential, we will just send, an action potential. That basically is just a 0-1 thing. For artificial neuron, it's different because we cannot do this 0-1 thing. We can, but we cannot train it. As we will see later, everything has to be differentiable. So that's why, we are using this sigmoid function here, where it's basically, if you look at it, it's basically sort of like a 0-1 switch. So everything, so at the x-axis is the input. So, all the input, if everything, accumulate together, the sum is larger than 0, then you want to send a 1. If everything sum up together is lower than 0, you want to send a 0. So ideally, it should be something like, it should be something like this, 0 all the way and 1 all the way for the positive side. But sigmoid is basically just a smooth version of that. So, think about how you turn a 0-1 step function into something that's less sharp. So that's basically the idea. How can I get rid of that? Cool. Oh, I do have a slide for that. So why sigmoid? So basically what we want to see is, this is original what we want, a unit step function. So basically everything that's below the threshold, we want 0. Everything beyond 0, we want a 1. So this is the threshold. So now these two things are a little bit different. For this, the threshold will be the horizontal one, but now we flip it somehow. So the x-axis will be the accumulated, accumulated like signals. Accumulated stimulus, I guess that's a better way to say it. Accumulated stimulus. So all the stimulus, if it's together, the sum is larger than 0, we want a 1 as the output. If it's less than 0, then we want the 0 as an output. So this is non-differentiable, so that's not good for all the deep learning stuff, and that's why we turn it into a sigmoid, so that is smoother. This is the function for sigmoid. There's the reason why we are using sigmoid. There's a whole lot of math why we're using this function, but most of the case, we would just take it. There's some good benefit of sigmoid. That's why we use it. Also, why bias them? Because all non-zero outputs, when all outputs are 0, if we don't have bias them. So bias them would be helpful when you have everything 0, but you still want some output value. So that's the importance of bias them. Cool. So again, artificial versus human neuron. Some similarities, but also some differences. The way how they accumulate surrounding stimulus and surrounding signals together, and do some weighted sum, and then to figure out whether you want to send an output signal. Then you send the output signal and connect to another cells. And so that's pretty much how we build this artificial neural networks. So artificial neural networks, it's different from human neural networks in that artificial neural network, we have layers by layers, as you can see here. Usually we build these artificial layers, artificial neural network layers by layers. For human brains, even though we have some evidence that there are some layers in our brains, most likely there's a lot of like loops and a lot of like different structure in our human brain. So it's not that simple as, layer wise. And also it's much more complex in the way how human brains, the neurons connect to one another. There's tons of things we could talk about. What's the difference between two? But that's not the key point of this part of how we should understand artificial neural network. Cool. So I guess we can move forward and get into more details about what a neural network could be like. So the first, the most basic form of deep neural networks is this thing called fully connected feed-forward network. So basically, this is the thing that you see again and again. Cool. So we can actually do some math to sort of like, at some point, you might look into this. I think there's another PA where we will actually train one of these neural network, even if it's not in this form, but you can sort of get a sense what this math formulation would help in determining what we want to do. So the way how we look at these neural network as a mathematic operation is that look at an input. It's just some input and output. That's the most important part. And all the middle layers is just to try to formulate a mapping between inputs and outputs. So that's one of the most important concept in deep learning is that any single neural network with some weights, it's just a function. It's just a mapping between inputs and outputs. Everything in between is just a fancy, a way to approximate that function. So the way how we could sort of like mathematically formulate this is that now you take a look at all the neuron, composition. So in the first layer, we have like x1 to xn. Those are all the numbers. So for x1, x2, x3, all the way to xn. So we can just say this is like a vector. We have a bunch of numbers. And how we gonna compute this first, output when we send this signal to the next layer? You can actually see that it's basically a matrix vector computation where you want to say x1 times w11. This is the first weight. W12, that's the second weight. W13, all the way to w1n. So you can actually just do a dot product between x1 all the way to xn with w11 all the way to w1n. So you can think about this as just like the weight function for all the connection to the first neuron. So we can basically view this as w1 dot x plus b1. So we also have a bias stem. So you can pretty much use the same idea to compute all the other neurons. So for the second neuron, it's just a bunch of other weights. So now it will be W21 all the way to W2M. So this is W21, W22, W23, W2M. So a whole new set of weights. But basically, the input is the same thing, just that now you times it with different ways so that you get the second neuron output. So basically, you can do the same thing again and again. But the idea is that this can actually be formulated as a matrix computation so that it could be efficiently computed on the laptop. So, if you look at this, you can turn it into a matrix computation. So, you take W11 all the way to W1n and WN1 all the way to WNN. So this matrix basically shows all the n by n weights between these n neurons and these n neurons. So pretty much what you need is all the orange values, that's the x, and you need all the weights between, that's the purple stuff, that's the matrix, and then you can get the outputs with some bias stem. So the idea here is that, W11 to W1n now is the first thing we talk about. The thing So I guess the whole idea is just to show you why there's some metrics going on in this graph. You know, how you compute the first output could be done in this metrics, um, you know, computation. And for this metric computation, you get the last neuron. So basically, there's some metrics computation going on here, and that's why we are using the GPUs to do this. So the difference between CPU and GPU, think about it, is like for CPU, if you want to compute the the dot product between this and this, you have to go through, W11 times X1, W12 times X2, all the way to W1n times Xn, and then you have to go through, n by n computation. But for, GPU, basically what we need to do is that, each single unit of the GPU is doing all the computation. So, it's like parallel computing, huge number of computation all at the same time. So it can run, W11 times X1 and WNN times Xn at the same time on the GPU. So the GPU, the idea of GPU and CPU is that CPU is much faster, but you can do everything. You can only do everything sequentially. GPU is much slower for each single unit, but you can compute everything in parallel. So metrics computation is one of the things that can be very efficiently done on a GPU. So think about it. Why deep learning? All about deep learning nowadays is actually not because people haven't think about deep learning for years. So people actually think about deep learning for decades. It's only happening recently. All these big models. Part of it is because the hardware innovation. Now we have much faster GPUs. That's not possible in the past. So that we can drive all these computation much more frequent efficiently. Anyway, we won't go into details, but I guess the idea is to just to give you the flavor that, actually all these neural network can be formulated into some metrics computation, which can be effectively computed using GPUs. And, we can formulate them all the way in the same. So to get the first hidden layers, the the first neuron outputs, you can do, the X is the input. You have all the weight, the matrix. If you do a dot product, and then added a bias stem, and then apply the nonlinear, sigmoid function or whatever other activation function, and you can pretty much do the same thing for the second layers. So now you have H1, this first hidden layer. You apply the same idea, do a dot product between that with the second, weight function, weight matrix, and then a bias stem to get the next neuron. So pretty much you can do the same thing all the way until you reach the last one. So this is basically, how you can view a neural network as a bunch of, mathematical computation, mostly, weight, matrix, dot product with the vector that you have, and then some summation with the bias vector, and then you do the activation function. So, this doesn't look like anything we have, because usually we will have something like this where you have different numbers of neurons in between. And, depending on what you are mapping. So think about the case where we are doing, estimating the bear's, age and weight based on how much they eat, how long they sleep, maybe how fast they run. So 3 variables as our inputs, 2 variables as our outputs. So it depends on what exact task you are trying to solve. So in that case, pretty much everything is the same, just that now these weights have different shape. And that's all the troubles when you want to do all these. And that's why we have all the package to handle this. But basically, they're the same, just that, the matrix now has different shape and all the vectors have different shape. But pretty much you can still do it with all the matrix computation. So that brings us to the next topic, where Now, with all these mathematical things, we don't really care, most of the case where we just want to define um, a neural network as this shape. So, now we can actually just view everything in between as some function x. We don't really care about what's going on in between. We want to figure out what's the best, setup so that this function best approximate this mapping that we know. And we want to learn this mapping from the data. So that's the correct way to look at neural networks. So neural networks are just parameterized functions. So a neural network represents a set of functions. And we usually, denote it like this, f theta x, and theta are all the parameters. And so what are the parameters here? Any thoughts? What are the parameters we are talking about here? Yep. So that's essentially what we are talking about. So there's a common misconception. So it's a little bit different from what we are doing. So we have like X and Y. So this Fx will, go from X to Y. And this theta is something other than X and Y. The theta is actually all the weights and bias and everything that you can train this model for. So the idea now is that we have X, we have OI, as we talk about machine learning, is just trying to learn this mapping. And what we want to do is to approximate the things in the middle, this neural network, as good as possible so that it match that mapping. So this is the whole idea of, deep learning, basically, that we have a bunch of functions that's defined by all these parameters. Think about, different weights, different bias. These could be different values. So some of those are bad, some of those are better. And basically what we're trying to do is to find the best option from all these possible set of functions. Cool. So this pretty much is what we want to do when we want to train the neural network. So the idea is that we build a neural network, something like this. It would define a huge set of functions where, all the parameters, the weights and bias will each combination of those parameters so will define one single possible function. And now we want to define the objective. So we want to see what's good for a function. So think about the case of, Bayer weight and age estimation. And, previously we talked about how we define the objective. So, stock price, we could see, how good it is, how far away it is from the actual prediction. Think about, dog and cat classification. We can look at the accuracy, but define what is good for the function. And then what we want to do is find the optimal parameters, which leads to the best function. So, in this case, what we want to see is that, we have X and we go through this big set of function. Each single combination of the parameters will give you a specific function. Some of those are good, some of those are bad. But basically, now you see that these Y has a hat. So usually we will use Y hat as the prediction, the estimation, and compare that with our, real, weights and, age of the bear. Then we can actually define an objective, whether those are good or bad. And now we basically want to use this objective function to find the optimal parameters. So this figure basically shows the key components of deep learning model. So again, a neural network is not, a single function. A neural network is only a single function when you have a specific weights and bias. So a neural network will represent a set of functions. And our goal is to, look at the estimation and the real ground truths so that we can define whether those are good or bad. And then we use that as the signal to find the optimal parameters that give us the best, the best function or estimation of that function. Questions? Good. Let's just proceed and see if we will have more questions. Cool. And I guess we also sort of like covered this, did we? No, no. I think I just provide some examples. So one of the two, not one of the two of the most iconic tags for the machine learning, deep learning is regression and classification. Their definitions are very simple, but sometimes it's a little bit hard to see why a text is regression and classification. We'll see later. So regression is anything that's, the output will be continuous. So think about age of a cat. It will be 5, but you can also be more specific. It could be 5.1, 6.9, 7.2, whatever number that is. For classification, now we want to see, something binary or something, categorical or, something that's discrete. So in this case, is human, yes or no? So, regression models output a number, classification outputs a label. That's the key. So some of the most simple example, think about stock price prediction. What we want to do is going from 0 all the way to infinite. And we basically just want to guess what the number is. So this will be regression, of course, because we are estimating a number. But now this is a little bit more tricky. Think about depth estimation, where we want to look at an image and then we want to see, for each single pixel, what would be the estimated depth. So in this case, it's actually doing regressions on each single pixel. There are W times H pixels, and we want to estimate the depth for each single pixel. So if you look at this image, especially on the top, you see the sofa is closer to you, these furniture is closer to you, but at the end, there's this bathroom. So that's it's like very reddish because that's further away. And in this case, this is the shape of the classroom. So the corner here is the furthest away, and this desk is the closest. So the desk will be blue, and the corner will be in dark red. So, a little bit non-intuitive, but, depth estimation is essentially a regression model where we are doing a number estimation on each single pixel. For classification, I guess the most simplest case is that, we are doing some classification. So in this case, animal classification, the output would be either cat, dog, bird, bear, or a bird. So your function is just to look at this image and output what the category that would be. Or more, iconic, this is like MNIST handwritten digit classification, oftentimes used as the, golden standard, or I guess not golden standard, more like, the benchmark for machine learning models. So you want to look at, an image of 28 by 28 pixels, grayscale pixels of all the different handwritten digits. And you want to output what that category is. So this is not a regression problem, even though the outputs are numbers, because now we only have 10 different possibilities, 0, 1, 2, all the way to 9. So that's different from regression, because regression is an actual number. In this case, we are actually doing a class. We also have like spam builder, where looking at some text, and you want to detect whether it's a spam or not spam. Cool. So that's basically some examples of classification and regression. And sometimes it's a little bit tricky to see whether something is classification or regression. You have to look at the outputs of those numbers. Cool. So I guess we can dive deeper into why activation functions. So we talk a little bit about, that sigmoid thing, but we don't really see why we need activation functions. So as we said, inside a neuron, what we're essentially doing is just a weighted sum of all the inputs. So this is important because, as I said, a neural network is a set of functions. Each single function, each single combination of weight and bias will determine a specific function. And our goal is to find the best function out of those possibilities. So, inside the neuron, this is what it looks like. We will have weighted sums and of the inputs added with a bias term. And there's this weird, activation function here. So we don't necessarily know for now what's going on. We just take it that there's this activation function, which acts sort of like a softened version of that, thresholding thing, the potential threshold for human brains. But why do we need that? So that's essentially what we want to see here. So the first reason is that we want to introduce some nonlinearity. So think about a model that's that's just a linear function. It's a weighted sum of the inputs plus a bias term. But there's tons of different possibility of nonlinear functions. So some of the iconic one is the inverse, square, exponential, or even the correlation between different variables. So all of these cannot be, modeled by just a linear function. And that's why we want to introduce some nonlinearity into our model. So that's the first thing. But we will see a better explanation later. So, without so this is the way how we can sort of like expand our mathematical formulation. And as I said, to determine the first outputs, we can do something like this, a matrix times the input x plus the bias term, and going through some nonlinearity, you can get the first layer. But this is what we have all the way. So with the first layer, we can do some matrix computation, bias term, nonlinearity. You get the first layer output. Now take the first layer output and times it with another weight matrix plus some bias term, do the nonlinearity, you get the second layer, second hidden layer output. And then you take the second layer output so that you do some computation, you get the third layer outputs, all the way until you have the last layer, last hidden layer, and you do the same computation so that you get the output y. So you can actually just expand that again and again. So you take these things, so y equal to this sigmoid WL times HL minus 1 plus BL. Anyway, it looks kind of terrifying, but the idea, you will just see it here, that we can just replace the things with the thing. So, once you expand it again and again, basically, you can define the last layer all the way through a chain, optimization, computation matrix, blah, 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 whatever, all the way down to X here in the middle. So you have X, you do some matrix, bias, and then nonlinearity. Now you take this and then weight, bias turn, nonlinearity, weight, bias turn, nonlinearity, all the way you expand, L times so that you reach the final layer. So, technically, as we said, a neural network is just a function, a set of functions for X to Y. So this basically just show you the exact format when we are looking into fully connected layers. Because, we have Y as the output, we have X as the inputs, everything else is determined. and we want to find the best option for these W and B, basically. Cool. So now let's see what happened if we don't have, these activation functions. So the activation function is the orange things here. If we don't have these activation function, if it's just linear, everything just gone. So this just turned into a linear function. Because if you expand this, it's just a big matrix computation without any linearity. So this will be down to, degraded into just a linear function, which is not good because, there's tons of different nonlinear function that we want to model. Cool. I guess that's two mathematics way of explaining stuff. So I guess I could show you another examples how we can do it. So these are some of the commonly used activation functions: sigmoid, hyperbolic tangent, and ReLU. So you can sort of see they all have a similar kind of shape where there's somewhere flat and there's somewhere some slope. And for sigmoid and hyperbolic tangent, there's this, another flat region. But for ReLU, you can think about it, it's just like a sigmoid, but without this, flat part again. So ReLU is actually nowadays what people have been using most frequently. Actually not sigmoid or hyperbolic tangent anymore. So this ReLU function, and this ReLU function actually have a very easy way so that we can look at it. So this is a way to look at how ReLUs actually approximate a function as a piecewise linear functions. So let's see if this is the function that we want to sort of approximate. So we can actually turn it into this sort of like piecewise linear function where we just have all these linear estimation of the function. So what the ReLUs want to do is that look at this figure. At first, everything is 0. And now we want to turn it a little bit up so that we now use this ReLU function to approximate the first part of this function. And now you can go to the second turning point. Now you can use another ReLU to move it a little bit higher. So look at this, that in the middle part, this slope, if you take this plus this, you get the, this smaller slope. But now going to this region, now you are at the right of the first ReLU. You are also at the right of the second ReLU. So the two ReLU will add it up together so that you get a double slope. So now you move. So think about this as a different case of Fourier transform, where Fourier transform you want to decompose a function into so many different components. Now you are using these ReLUs to try to compose this functions. So now if you go to this turning point where we want to place the next ReLU, now how you want to turn it away. So you can actually just add a very, very deep, going down ReLU. Because if you time ReLU negatively, you can just turn it into the opposite way. So now, at this point, still, this ReLU is, doing nothing. And you have two slopes. So these things will be double the slope. And now at this place, you have like one up, but very deep down. So it actually gives you this slope. So you basically just do the same thing again and again. Now, at this point, you want to add another ReLU that will be very, very high up, very steep slope upward, so that everything's summed together will give you this slope. So this sort of like give you the sense, what ReLU is doing, and it's the same for the sigmoid function, even though it's a little bit trickier because sigmoid will turn back into this flat things again. But you can sort of like imagine what we are essentially trying to do is sort of like the inverse of Fourier transform, where now we have a bunch of ReLU that's determined by the neural network. But basically, the neural network is trying to place these ReLU at different places. Left and right, you want to do the offset. You also want to change the slope. That all determined by the weight. But basically, you want to decompose this function into four different values so that it sums up into this linear function. And the idea of neural network is to try to see how you adjust all these slopes and also the x and y, the offsets of these functions. Does that give you the sense of what activation function is? So, activation functions, there are two things. One is that without it, there's no nonlinearity. So there's no way you can approximate some other things. But at the same time, ReLUs also provide us a very intuitive way to look into what this activation function is doing. Because essentially, ReLU is just approximating functions into piecewise linear functions. So, original, something like this. But you can actually use four ReLUs so that together they sum up into the blue piecewise function that approximate the curve in the back. So think about why we want more parameters, why we want more parameters in a neural network, because now you can actually place more ReLUs so that it will be a smoother, a more, a better approximation of that linear function at the back, underlying the curve. So hopefully that sort of like persuade you why we need that ReLU sync. But nowadays, most of the deep learning models, are using this ReLU activation function. So there's also a tons of, papers talking about this piecewise linear functions perspective of nowadays neural networks. So nowadays neural network could be just trying to break down all the complex functions into piecewise linear functions as an estimation. Questions? Cool. Again, I guess these are too mathematic, but I guess the biggest concept here we want to know is that any single neural network is just a set of functions, and we want to try to find the best functions. And these are just explanation why these neural networks are how these neural networks are defining all these functions. Cool. So now after we talk about these neural network thing, there's this one thing that's always be confusing for anyone who started with deep learning. And at first, I was also fascinated about this theorem, and then we are like, why? Why are we doing this? So this theorem is called universal approximation theorem. Basically, it says a neural network with one single hidden layer. So forget about all the metric things, layer by layer thing. One hidden layer can approximate any continuous function given sufficient hidden neurons and appropriate activation functions. So in this case, appropriate activation functions is very vaguely defined, but sigmoid ReLUs are good activation functions here. So basically it says a neural network with one hidden layer can approximate any continuous function given sufficient number of hidden neurons with sigmoid or ReLUs. So why do we want to go deep if this is the case? So there's always this debate of, shallow versus deep neural networks. So what's the difference? So for shallow neural network, we oftentimes look at this, we have three as the inputs, 2 as the outputs, we could basically just grab, 9 hidden neurons here. So if you look at the connection, so the connection, each connection is just a weight. So, the weight sort of define how many parameter you need for this neural network. So we oftentimes look at this connection to see how big this model is rather than the number of neurons, because neurons doesn't tell you the size of a model. So in this case, 45 connections, but you can also, turn it into a very deep neural network where you have three neurons for 3 layers and two for 3 layers. And if you calculate the number of connections, so this would be 3 times 3, 3 times 3, 3 times 3, 3 times 2, 2 times 2, 2 times 2, 2 times 2. So if you sum them up, actually also sums to 45 connections. So these two actually have the same, number of parameters. Basically we say they are of the same model size. And we also have something in between, in this case, 5, 3, 3. So you have 3 times 5 weight, 5 times 3 weight, 3 times 3 weight, and 3 times 2 weight. So this again is like 45 connections. So, all these 3 models have the same number of parameters and have the same model size. And that's basically what we observe in real life. So usually shallow neural networks are less expressive. By less expressive, what we mean is like less parameter efficient. And parameter efficient is a very tricky things to understand. So basically is that, the set of functions that you can represent by this neural network is usually smaller than this thing, because there are more nonlinearity going on in this case. So usually this is like in practice. There are a lot of like machine learning theory looking into why this is the case. But in practice, as you will see, when you train the model, is that the deeper it goes, the more expressive it is. But it's much harder to train, as we will see later. So at the thing at the left is what we call shallow neural networks, and the things we call at the right is deep neural networks. So how deep is deep enough? Do you get the point of that? Anyway, how deep is deep enough? So deeper is not always better, but this is like 1998. If you look at the progress of how things work, 1998, 1, 2, 3, 4, 5, 6, 7, 7 layer. This is the LaNet, this Yann LeCun convolutional neural network. So this is how they got the Nobel Prize. And then we have AlexNet, much larger, but still not too bad. VGG19, this is like 2015. This is, still 19 layers only. But now we have like ResNet 2015. Now this is like 34 layer residual net. So now, everything just go deeper and deeper. So it depends on the actual numbers of parameters, and there's also optimization difficulties, and also depends on the data set. And lastly, about the inductive bias of the model. We will get to that later. But anyway, usually we mark 2012 as the sort of like inception of deep learning. So you can see that, even in 1998, people have been looking into deep learning, but nothing big has been done. Pretty slow progress, but after 2012, usually marked by AlexNet and all the following, new deep learning models. And now deep learning models becomes very, very large. So this is also one of the plots that people usually look at. So at the y-axis is the number of operations. So that's, how many computation it requires to work with neural network. And on the y-axis, so this will be sort of like not model size, like how computationally intense it is. And the circle size would be the size of the model. And the y-axis is the accuracy. So the higher, the better. Oh, I have these. Classification accuracy, computational cost, and the size is the model size. So at the top left is low cost, high performance. At the bottom right is high cost, low performance. So you can see that from 2012, 2014, 2015. Now we have all sort of like different options so that you can see what are the different options. So you could aim for something very high accuracy but computationally costly, but you can also look at something less accurate but with much lower computation costs. Cool. So I guess these are the last few slides. So to get things even more complex, we sort of like in this previous slides, we talk about all these layer by layer neural networks. And as I said, human brains doesn't work like that. So we don't necessarily want neural networks to be always layer by layer. So we will have something like this, skip connections, which will, sort of like a highway. We go from this neuron directly to the final neuron. So these are skip connections. In practice, look at the model here. You see all these, highway connections. So these are skip connections. So it's practically very useful. We also have feedback loops. This is much trickier because you will need to sort of like redefine the whole idea. And that's essentially how recurrent neural network is based on. Cool. So I guess we cover most of the fundamental part of deep learning. So we talk about the difference between artificial neurons and human neurons, similar and different in some sense. We talk about how we can just combine a bunch of neurons into a artificial neural networks that they didn't actually work like human brains, but hopefully good enough. And we look at all the math, but math is not the most important part. The most important part that is that a neural network represents a set of functions rather than one single function. So each single combination of parameters, weights, and biases will determine a specific function. And our goal is to compare the estimation to the actual ground truths that you have from your data so that you determine whether it's good or bad, and you use those to select or to find or to optimize or to train the model to find the optimal parameters that define the best function that you have. So, next class, we'll basically just look into this. We can see, how we can determine other types of neural network. As we just saw, there could be loops, there could be skip connection, there could be a bunch of way you can build a neural network that doesn't has always to be this like layer by layer like. But basically, a neural network will just defines a set of functions. And then you define the objective functions where you determine what is good for a function. And then you would want to find the optimal parameters, which leads to the best function. Cool. And to sort of like give you a sense why these activation function can help in approximating a function through piecewise linear functions. Cool. So I guess that's it. So next class, we will dive a little bit deeper into deep learning to decompose all the components. Essentially, we will look into gradient descent and backpropagation, two of the most important things in deep learning. But anyway, the same high-level idea is the same. We just want to dive a little deeper into what each step is so that you get a sense more grounded into what it is. Cool. See you on Wednesday.